Okay, so can you see my screen? Can you hear my voice?
Nampak Doktor?
Okay, terima kasih. So last week we have stopped until this slide. Okay, maybe I will go back to the previous slides, starting from here, so that we can refresh again what we have learned last week. Okay, so last week we have learned until the general equations for phase modulation and also for the frequency modulation. Okay, and if you remember that the general equation for angle modulation, I go back for a few slides before. So the general equation for angle modulation is defined as V function of time, okay, which is equal to Vc sine 2 pi fct plus theta t. Okay, and this is from the Wayne Thomas's book, where he used a sine function. And if you read from other literature books, you will see that some of them use a cosine function. Okay, so tidak ada masalah, no problem. Okay, we can use cosine, we can use sine function. Okay, and as I already highlight last week, that I would highly suggest to you to put a big bracket over here. Okay, in order to avoid a careless mistake. Okay, because all of this 2 pi fct plus theta t is the component of sine function or cosine function. Okay, semua ini adalah milik kepada sine function dalam kes ini. Okay, dan if you see from the next slides, okay, what is the theta t? Okay, from the general equations, you will see that theta t will change in accordance with the amplitude variation of the input signal. Theta t ini berubah-ubah berkadaran dengan perubahan amplitude daripada information signal. Okay, so we have seen previously, we have seen about theta t. Okay, and kita dah lihat theta t sebelum ni, theta t. And we also have seen about theta prime t, which is equal to the first derivation of theta t, d theta t dt. Okay, pembezaan daripada theta t terhadap masa, you akan dapat theta prime t. Okay, so theta t dalam radian, dalam radian, dan theta prime t dalam radian per second. Okay, ataupun dalam sebutan hertz. Okay, and if you want to find the theta t, okay, based on the theta prime t function, so that means we need to do the integral of theta prime t dt. Okay, so kalau kita nak dapatkan semula theta t, kita perlu buat proses kamiran. Okay, and what is the theta t and theta prime t? Theta t kita dah lihat sebelum ni, theta t adalah instantaneous phase deviation, manakala theta prime t is the instantaneous frequency deviation. Okay, so ini ada dinyatakan di sini. Okay, instantaneous frequency deviation and also instantaneous phase deviation. So what is theta t? Theta t is equal to Kp Vmt, where Kp is the phase deviation sensitivity parameter, Kp. And theta prime t is equal to Kf Vmt. Kf is the frequency deviation sensitivity parameter. Okay, kedua-dua ini adalah constant parameter. Okay. And you see that from here, what is the unit for Kp? The unit for Kp is radian per volt, where it is defined as the difference of phase of the carrier divided with the difference of voltage of the carrier. Okay, so unitnya adalah radian per volt untuk Kp. What about Kf? Kf is radian per second per volt, which is defined as the difference of omega of the carrier divided with the difference of voltage of the carrier. So remember that the changes happens in the carrier, not in the information signal. Bukan dalam information signal. Okay, and I already told you last week that this kind of question has been come out in the previous exam. Okay, where the students has been asked about the sensitivity parameter, Kp or Kf, I don't remember. And that questions, saya ulang balik, maknanya dalam soalan exam yang lepas, pernah ditanya, contoh soalan tentang Kf, where we ask about frequency modulations questions, okay? And that questions gave a table, okay, about the readings from the modulator, from the FM modulator, where you are given, for example, omega and also the voltage. Okay. Ini pernah ditanya. And this is a reading, bacaan yang diambil daripada FM modulator. Okay. So ini where this is in term of radian per second. This is in term of volt. Okay. And the question gave x1, x2, I don't remember the value. Okay, adalah value-nya. And similar with the voltage, y1, y2, y3. Okay, and remember that in order to find Kf, okay, it is defined as the difference of omega divided with the difference of voltage. That means you can find the difference between two consecutive value. Okay, kita boleh cari perbezaan antara dua value yang bersebelahan, sama ada x1 dan x2 ataupun x2 dan juga x3. Okay, for example, we can find the Kf equal to x2 minus x1 divided with y2 minus y1. Okay, and this is we will get this as a radian. And so this is radian. So radian per second per volt. Okay, so ini unitnya lah. Okay, and actually you can also do either like this. Okay, x3 minus x2 boleh juga. Y3 minus y2. Okay, the thing is that we need to subtract two consecutive values, nilai yang bersebelahan, sama ada x2 tolak x1 atau x3 tolak x2. Okay, y2 tolak y1 ataupun y3 tolak y2. Dia mestilah nilai yang bersebelahan kerana ini adalah linear value. Okay, so kita akan dia sebenarnya adalah satu nilai yang linear, yang mana you akan dapat jawapan yang sama lah, sebab Kf ini adalah constant parameter. Okay, so that is about the Kf. Okay, so when we get the Kf, then we can define the complete equation of Fm, frequency modulation. And when we get the value of Kp, then we can define the equation of phase modulation. Okay, Kf ini digunakan dalam Fm, frequency modulation. Kp digunakan dalam phase modulation. Okay. And about this, I already explained previously about theta t. How you can get theta t is the first integral of theta prime t. Okay, so kita kamirkan Kf Vmt. What is Vmt? Again, Vmt macam biasalah, Vmt sama ada Vm sin, okay, Vm sin 2 pi Fmt, or you can also use a cosine, M cos 2 pi Fmt. Okay, so you see that dikeluarkan nilai Kf kerana Kf adalah constant parameter. Okay. And from there, we can define the complete equation of phase modulation. So phase modulation is I can say that the equation is more easier compared to the FM because it is directly defined from the general equation. Okay, didefinkan secara langsung daripada general equation. Okay, so from the general equation, VC sine omega CT plus theta T. Now we can convert theta T into Kp VMT. So jadilah seperti ini. Okay, so therefore we can rewrite the equation to become VC sine. Remember to put big bracket. Okay, omega CT. So this is actually 2 pi FCT. Okay, plus. So this is, we want to define phase modulation equation. So therefore we need to use Kp. Okay, gantikan theta T dengan Kp VMT. Okay, so Kp VMT. VMT is Vm sine omega mt. So this is actually 2 pi Fm T. Close big bracket. Finish. So this is the equation for phase modulation. Okay, ini adalah persamaan umum untuk phase modulation. Okay, and then what? How can we define the frequency modulation equation? So from the general equation, we can define the frequency modulation equation. Daripada persamaan umum angle modulation, kita boleh define frequency modulation equation. Okay, so from the general equation like this, okay, this is the general equation. We need to change the theta T. Okay, so theta T is we can use the integral of theta prime T. Okay, kita perlu gantikan theta T dengan integral of theta prime T. What is theta prime T? Theta prime T is equal to Kf VMT. Okay, theta prime T bersamaan dengan Kf VMT. Maka kita kamirkanlah Kf VMT. Okay, so VMT is Vm sine omega mt. So we can put Kf and Vm outside because both of these are the constant parameters. Okay, kita letak di luar kerana dia adalah constant parameters. Okay, remember that omega CT adalah 2 pi FCT. Okay, so integral sama juga di sini. This is 2 pi FMT. Okay, so we integrate sine, we're gonna get a negative cos. Okay, so therefore the final answer is VC sine big bracket omega CT, or you can write 2 pi FCT, okay, minus KF Bm over omega m. Tadi kamiran daripada sin kita akan dapat negative cos dibahagikan dengan omega m. Okay, so omega m ini muncul disebabkan oleh proses kamiran. Okay, so omega m is actually you can write omega m, or you can write like this 2 pi Fm. Sorry, or you can write 2 pi Fm. Okay, sama ada nak tulis omega m ataupun 2 pi Fm. Okay, cos omega m. So close big bracket. So this is the general equation for frequency modulation. Tadi daripada persamaan umum angle modulation, kita terbitkan persamaan Fm. Finish. Okay. Ini pernah ditanya dalam exam beberapa semester yang lepas, where we ask the students to define the FM equations. Okay. In the questions actually we give the values. Okay, kita berikanlah dia punya nilai, contoh 100 sin, ini berapa frekuensinya, 2 pi, ini frekuensi F, ada nilai lah. Okay, plus nilai Vm berapa, ini kita ada berikan nilai Vm berapa, nilai Fm berapa. So sorry, kejap. So dalam equation, dalam soalan itu dia ada memberikan nilai Vm, Fm, Ada diberikan nilai VC dan juga FC. So you need to define the complete equation of the FM. Okay. At that time is a face-to-face exam, so tidak boleh buka buku. So you need to understand about how to define the complete equation of FM based on the general equation of angle modulation. Okay. So you kena terbitkan persamaan itu pernah ditanya. So dalam example ini diberikan dalam sebutan variable VC, 2 pi FCT, so tidak ada value. So apabila dalam soalan kita berikan dalam ada nilainya lah. So masukkan nilai-nilainya. So sekarang ni kita nampak dalam bentuk abstract sebenarnya, dalam bentuk variable. Nanti ada example seterusnya. Okay. So now the thing is that you need to understand how to elaborate from the general equation of angle modulation to become the frequency modulation equation. Okay. So kalau ada soalan, please ask me question if you have question. If you don't understand, you can ask question. Okay. So the first exercise 3.1, you need to derive PM and also PM signal using both cosine and cosine wave signal. Dia ada bagi tahulah. Kedua-duanya cosine, maknanya general equation menggunakan cos, VMT menggunakan cos. Okay. So for PM, remember for phase modulation, we need to change theta t with Kp VMT. Okay, so therefore we change it into Kp VMT. Maka kita akan dapat VC cos, remember big bracket. Okay, remember to write big bracket omega CT, or you can write 2 pi FCT. Boleh juga tulis 2 pi FCT plus Kp. So tadi kita dah tukar Kp Vm cos omega mt. So this omega mt is equal to 2 pi Fm t. Okay. And then what? For Fm, frequency modulation. So from the general equation, we need to change theta t into integral of theta prime t. Okay, so ini sebenarnya adalah integral daripada theta prime t dt. Okay, so theta prime adalah bersamaan dengan kf vmt. Okay, so therefore integral of kf vm cos omega mt. Okay. So put outside the kf vm because both of these are constant parameters. So we integrate cosine function. Integral of cosine, we're gonna get positive sine over omega m. Okay. So therefore we get kf vm over omega m. So this is the final the equation for frequency modulation. Okay. And remember, the thing is you need to do big bracket. Don't forget about the big bracket. Omega CT, you can write 2 pi FCT. Boleh juga. KF, VM, omega M, you can replace with 2 pi FM. Boleh ya, nak gunakan omega M boleh. Nak gunakan 2 pi F pun boleh. No problem. Okay. So over here, you can also use, if you want, 2 pi FM. Sorry, 2 pi FMT. Kena ada T lah. Okay. So this is the first exercise. Ada soalan? Kalau tak ada soalan, saya akan teruskan. Okay. This is about the changes of carrier frequency in accordance with the amplitude variation of the VMT. Nampak So now we want to see what happened to the carrier frequency when the VMT change. Okay, apa yang berlaku sebenarnya kepada frekuensi carrier apabila VMT ini berubah-ubah dia punya amplitude. So perhatikan di sini, perhatikan. So you see that this picture, from this picture we want to see the carrier, the changes of the carrier in accordance with the changes of VMT. So bahagian atas ini dia nak tunjukkan bahawa ni paksi X saya katalah ni paksi X ini which is F so this is actually referring to FC. Dia merujuk kepada frekuensi carrier. Okay. So frequency carrier at the beginning is at Fc. Pada asalnya carrier mempunyai frekuensi Fc. And due to this modulation effect with the information signal, the frequency or the phase of the carrier change in accordance with the amplitude variation of the input message. So di sini dia nak tunjukkan perubahan frekuensi. Okay, the changes of frequency of the carrier. Okay, so you see that the carrier frequency change from Fc until Fc plus delta F, and also change from Fc until Fc minus delta F. So maknanya dia berubah-ubah dalam julat tertentu daripada keadaan rehat. So we call it, this is a rest frequency. Rest frequency is rehat rest. Rest frequency of carrier is at Fc, and then dia bergerak daripada Fc sehinggalah maksimum Fc plus delta F, sehinggalah maksimum sebelah minus, sebelah negatif is Fc minus negatif, Fc minus delta F. Okay, dia bukan nilai negatif, dia berkurang Fc minus delta F. So now we want to see what happened to the carrier frequency when the VMT moves, changes. Okay, you see that VMT, so this is, katalah ini satu lagi paksi okay, and we see that here this is a VMT moves from 0 until positive maximum. Okay, from 0 until positive maximum. What happened is that when the amplitude of the when the amplitude of the VMT is positive maximum, the carrier frequency change to Fc plus delta F maximum. Frekuensi yang tertinggi. Okay, and then what? VMT moves from positive maximum until reach the axis. Dan pada ketika itu dia Fc berada pada nilai rehat pada frekuensi Fc. Then VMT moves towards negative amplitude. Okay, towards negative amplitude. So what happened is that it becomes maximum. It becomes maximum. So you see that when VMT moves to, ini ada tulis negative VMT move to the negative VMT, maknanya dia bergerak ke arah ni, kalau saya lukis paksi macam ni lah so dia berada negative maximum. Okay, so at negative maximum of VMT, what happened to the carrier frequency? So carrier frequency is at the maximum negative. Okay, at the maximum negative. That means it's located at the Fc minus delta F, yang paling bawah, the minimum. That means the frequency of the carrier becomes minimum at that time. Pada ketika itu, and then when the VMT moves from negative maximum into 0 axis, so the carrier frequency becomes rest again, which is at Fc. Nampak So this process happens very quickly. Okay, this process happens quickly. It depends on the rate of Fm. Nampak ini kita nampak satu kitaran sahaja. So kalau Fm ini, if this Fm is for example 1000 Hertz, that means VMT change 1000 time, 1000 cycle per second. Maknanya ada graf seperti ini sebanyak 1000 kali dalam masa 1 saat. Dia berubah-ubah sebanyak 1000 cycle per second. Kalau 10,000, lagi banyak. Maknanya lagi laju perubahan itu. That means the carrier frequency change 10,000 times per second. So kadar perubahan frekuensi itu kadar perubahan frekuensi carrier bergantung kepada frekuensi input message. Nampak nanti kita akan lihat selepas ini. This picture. Nampak picture ni gambar ni. So this is to show you the difference between FM and also the PM. Okay, so you see that here the first graph is carrier signal, the second graph is information signal. Graph C here is for FM, this is FM. Graph D is for PM. So if you see graph C and D, we cannot differentiate which one is FM, which one is PM actually. Okay, kita tak boleh bezakan antara dua graf ini tanpa adanya graf pertama dan kedua. Nampak kalau saya tutup, kalau kamu tutup bahagian dua graf yang atas if you are only given graph C and D, you don't know which one is FM, which one is PM. Kita tak boleh bezakan. Okay, kita hanya boleh bezakan sekiranya kita diberikan graf yang pertama dan kedua. Barulah kita nampak dia punya perubahan. Okay. So the key here is graph B actually. Graph B ini memainkan peranan penting untuk melihat perubahan itu. Okay. So let's look for the FM graph. Kita nak lihat perubahan graph C berdasarkan graph B. Okay. So if you see from here, okay, before that this is a FC. So kalau you lihat graf pertama, frekuensi carrier itu stabil dia berada pada rest, maknanya frekuensi dia seragam. Okay, kalau kamu lihat graf pertama, frekuensi carrier itu seragam. Okay, kemudian ada graf B iaitu VMT. VMT berubahlah dia punya amplitude. Okay, kemudian untuk graf C, kita lihat graf C. So apa yang berlaku pada graf C adalah, graf C ini nanti kita akan lihat bahawa dia berubah disebabkan oleh perubahan amplitude yang paling ketara adalah pada maksimum positif dan juga maksimum negatif macam yang kita lihat tadi. Okey, tadi graf ini So tadi graf ini kadar perubahan yang ketara adalah pada maksimum positif of the VMT and also maximum negative of the VMT, barulah nampak perubahan ketara pada frekuensi carrier. Okay, tadi saya lupa nak beritahu bahawa perubahan ini yang pertama di sini ada delta F. Delta F dan juga delta F. So jarak perubahan frekuensi carrier ini adalah sebanyak 2 delta F. This is what we call as a carrier swing. Okay. So, parameter carrier swing ini selalu ditanya. Calculate the carrier swing. Okay, which is the 2 delta F. Okay. So, I go back to this slide. Okay. So, if you see from here, from this, okay, so carrier is at rest frequency. Nampak dia punya ni agak stabil, dia punya ni stabil frekuensinya stabil. Kemudian you see that this information signal moves from 0 until positive maximum. So what happened? You see that at this point, the carrier frequency is minimum because the ripple is at distance away. Gelombang ini berjarak-jarak paling jauh. Dia punya ripple itu jarak jauh. Dia renggang. Okay, so we can see that this is actually carrier frequency at this point is Fc minus delta F. Perubahan maksimum. Perubahan maksimum pada puncak positif atau puncak negatif daripada VMT. Itu adalah perubahan yang paling ketara pada carrier. Dalam kes ini, sekarang dia berada pada Fc minus delta F. Okay, and then what? The VMT moves from maximum positive until maximum negative. Before that, okay, saya padam sikit. Sebelum itu, dia lalu paksi X dulu, sorry. So VMT moves from maximum positive until zero axis, X axis. What happened to the carrier? Carrier frequency at this time is equal to FC, rest. Ini pun dia ada kata rest. Right? And then what? VMT moves from X-axis until negative maximum negative. What happened? When VMT moves to negative maximum, carrier frequency berada pada sangat tinggi. Daripada graf ini kita dah boleh nampak kerana gelombang itu rapat-rapat. So the ripple is very close to one another. Okay, dia rapat. So in this case, we can see that the carrier frequency is at its maximum value. Okay, perubahan yang ketara maksimum, iaitu dia berada pada Fc plus delta F. Nampak And then what? VMT move to X-axis, kembali kepada X-axis, and at this point carrier frequency is at rest frequency. Ini pun ada dinyatakan rest frequency. Dan seterusnya. Nampak so itu adalah berkenaan dengan FM, frequency modulation. Maknanya for frequency modulation, the changes, okay, the critical changes happen during positive maximum or during positive maximum or negative maximum of VMT. Perubahan yang paling ketara untuk FM adalah pada ketika VMT berada pada positive maximum ataupun berada pada negative maximum. Barulah berlakunya perubahan ketara pada FM signal. Nampak So the key here is the peak positive and peak negative. Itu dia punya kunci dia. Okay. Now we want to see about PM, phase modulation, graph D. Kita nak lihat graf D pula Biar saya padam yang atas sekejap. So saya padam yang ini. Okey, saya padam sekejap. Okay. So if you see from graph D, initially carrier is at rest frequency. Dalam keadaan rehat dia punya frekuensi stabil And then what? So you see that at the beginning here, you see that the VMT moves from 0 until positive maximum. Okay, assuming that the movement is from negative to positive. Katalah saya assume sebenarnya dia telah melalui beberapa fasa. Sebenarnya ini berubah daripada kosong ataupun negatif ke positif ataupun daripada kosong sehingga positif. Okey, so tak apalah, untuk elakkan keliru saya padamlah. Saya anggap tak adalah sekejap takut nanti kamu confuse. Okay, so this is movement from 0 until positive maximum. So what happened? So the critical point for PM, phase modulation, is actually happening at the zero axis. Perubahan ketara untuk PM ini berada pada zero axis of VMT. Kalau diperhatikan di sini, okay, di sini kalau you lihat nilai bentuk gelombang itu rapat-rapat, sangat rapat. Bermakna pada ketika ini berlakunya perubahan fasa yang sangat besar. Okay, ataupun carrier frequency itu menjadi tinggi. Okay, at this point dia adalah Fc plus delta F. Okay, Fc plus delta F. So saya tak nak guna delta F, saya nak guna delta theta supaya kita kaitkan dengan persamaan general equation tadi. Okay, delta. Actually theta. Ada yang nak tanya soalan ya? Betul? So sama ada nak gunakan theta C plus delta theta, or you want to write FC plus delta F. Boleh, tak ada masalah. Okay, so I want to relate this with the frequency as well. So that means at this point, siapa pelajar tolong mutekan you punya ni microphone. So at this point, carrier frequency is at FC plus delta F. Ada pelajar yang on mic ya, please mute your microphone please. Okay, so here is the carrier frequency is at maximum FC plus delta F. And then tolong mute microphone please. Okay. And then what? You see that the VMT moves from maximum positive until reaching the negative, reaching the x-axis. Dia bergerak ke arah daripada positif kepada negatif. Okay. So the critical point is here at zero crossing. So what happened at this point? Okay, so at this point, you see that it is a movement from positive to negative. Berlakunya perubahan daripada positif ke negatif. Maka nampak dia punya keywordnya adalah daripada positif ke negatif polarity berubah BMT. Maka pada output di sini adalah frekuensi carrier berubah menjadi minimum. Okay, so ini sepatutnya saya tunjuk yang tadi sekejap. Ada perubahan lagi satu. Sorry about that. So I padam yang ini saya padam yang ini. Saya ulang balik lah. So at the beginning tadi, pada x-axis, since this is movement from zero until positive, maka pada point yang awal ini, carrier frequency berada pada maximum kerana because we want to move from zero until positive. Dia bergerak ke arah positif. That means the frequency of the carrier becomes maximum. And when the VMT reach the positive maximum, what happened is that the carrier frequency is at rest, which is equal to FC. Apabila dia sampai kepada puncak positif, VMT mencapai kepada puncak positif, maka output phase modulation carriernya mempunyai frekuensi FC. Then the VMT moves until reaching the x-axis. And we're going to see that at this point pada x-axis ini VMT ini VMT. So at this point carrier frequency is equal to FC minus delta F. Menjadi minimum. Carrier frequency menjadi minimum. Kerana ini adalah perubahan daripada positif to negative. So the keyword here is changes from positive to negative polarity. So the output frequency becomes minimum. FC minus delta F. Okay. And then what? VMT moves again towards negative maximum. VMT berubah menjadi negative maximum. So what happened at the output for PM? So you see that here, the frequency here is at rest, FC. Nampak Maknanya pada setiap kali VMT mencapai nilai puncak positif ataupun negatif, frekuensi output pada PM untuk gelombang PM adalah berada pada rest. Setiap kali sampai puncak positif atau sampai puncak negatif, the output frequency of the carrier becomes FC, at rest. Nampak Then what? Then the VMT moves from negative peak until zero axis. So dia cross pada zero axis. So now the changes from negative to positive. Dia bergerak daripada negatif ke positif. So what happened? What happened at the output? The output becomes critical over here. You see that the ripple is close one another, rapat-rapat. So the carrier frequency at this point becomes Fc plus delta F. So carrier frequency is at the maximum value. Pada ketika zero crossing negatif ke positif, nilai carrier pada output menjadi maksimum, paling tinggi. Nampak So, dan seterusnya, when DMT moves again until maximum positive. So at this point, carrier become, at the output, the carrier frequency becomes rest. Nampak So maknanya, saya simpulkan So I can conclude that for PM, for phase modulation, the critical changes happens at zero crossing. Perubahan yang kritikal berlaku pada zero crossing of VMT untuk PM. Maknanya untuk phase modulation, perubahan gelombang PM itu berlaku ketara pada ketika zero crossing of VMT. VMT pada ketika dia melanggar, pada ketika dia berubah polarity pada paksi X, maka pada waktu itulah berlakunya perubahan yang ketara pada output. Nampak Berbeza dengan FM, berbeza dengan frequency modulation, where the critical changes happens at positive peak and negative peak of VMT. Untuk FM ni, FM frequency modulation wave, perubahan yang ketara adalah berlaku pada ketika VMT berada di puncak positif atau puncak negatif. Nampak So, boleh faham So, saya ulang balik For FM frequency modulation wave, the critical changes happens during the positive and negative peak of VMT. Perubahan ketara berlaku pada puncak positif dan puncak negatif daripada VMT. Apabila VMT sampai ke puncak positif atau sampai ke puncak negatif, maka pada ketika itu berlakunya perubahan yang kritikal, yang ketara pada carrier frequency output. Itu FM. Kemudian untuk PM, phase modulation, gelombang phase modulation ini mengalami perubahan yang ketara semasa VMT bergerak daripada positif ke negatif ataupun daripada negatif ke positif polarity. Maknanya perubahan PM wave ini berlaku yang kritikal pada ketika gelombang VMT ini memotong paksi X. Sama ada daripada polarity positif ke negatif atau negatif ke positif. Nampak Satu, PM berubah pada zero crossing, FM berubah pada ketika peak amplitude. Perubahan maksimum. Perubahan maksimum. Okay, so you should understand about this. Okay, macam mana nak membezakan antara dua gelombang ini. Okay, you should understand because this kind of question has been come out in the previous exam where the question asks about the FM and PM parameters. Pernah ditanya tentang gelombang-gelombang ini. Okay, so kalau nak tahu macam mana nak kenal pasti mana satu FM, mana satu PM, so you need to have the reference wave which is the VMT. VMT perlu menjadi reference wave supaya kita boleh bezakan antara PM dan juga FM. Okay. Do you have question about this? So adakah kamu faham macam mana nak membezakan antara FM wave dan juga PM wave? Faham tak? Kalau ada soalan boleh tanya. If you don't have question, I will move to the next slide. Okay. Do you need me to repeat again, or I can proceed? Ada respon?
Faham betul.
Okay, terima kasih. So kalau okay, saya akan move to the next slide. Okay. Phase deviation and modulation index. So now we want to see the modulation index about beta parameter. So kalau dilihat dalam equation ini, persamaan PM we can change into VC sin omega CT plus beta P. The word P here is for the phase modulation, beta P sin omega MP. Tadi kalau ingat sebenarnya beta P ini adalah KPVM. Dia gantikan KPVM. Tadi persamaan ni So KPVM ini digantikan dengan beta P. So beta P is the modulation index for phase modulation equation. Okay. So beta P adalah modulation index for PM. Okay. So unitnya adalah KP, dia adalah KPVM. Ini sebenarnya V besar, so please correct, this is supposed to be KPVM. And the unit is radians. Okay, unitnya adalah radian. So perhatikan dia punya modulation index has a unit. Okay, modulation indexnya mempunyai unit iaitu radians. Okay. So it represents the peak phase deviation in radians for phase modulated carrier known as modulation index. So one primary difference between PM and PM is how beta P is defined. Okay. So kita akan lihat macam mana bentuk modulation index untuk PM dan juga FM. So kalau PM, modulation index for PM, which is the beta P, okay, beta P is not related with the information message. Dia tidak berkaitan dengan FM. So kalau you lihat di sini dia KPVM, it is a KPVM. So it is not related with the modulating signal frequency, FM. So tak kira lah FM itu besar atau rendah, nilai modulation index masih sama. Okay. Berbeza dengan FM, okay, where the modulation index is beta F, and it is actually related, okay, it is related with the modulating signal frequency, FM. Dia berkait rapat. Nanti kita akan lihat bahawa di sini beta F is actually equal to ada nilai dia, nanti kita akan lihat slide berikutnya. Okay. So about beta P, tadi kita masih dalam beta P modulation index for PM. So we are still learning about PM, phase modulation. Okay. So remember that KP, ni kita dah lihat adalah phase deviation sensitivity parameter where the unit is radian per volt. You multiply with volt, so you will get radians. Ini sebenarnya unit This is a unit for KP. This is the unit for VM. Okay, so maknanya radian per volt you darabkan dengan volt, so you will get radians at the output. Okay, so the unit for beta P is radians. Okay. What about beta F? Nampak So beta F, this one. Remember about FM equations? FM equations tadi yang kita belajar tadi. Beta F, parameter di hadapan cos ini sebenarnya adalah KF VM over omega M. Or you can write KF VM over 2 pi FM. Okay, and here, if you see from here, the unit for kf is radian per second per volt. Multiply with volt, so you will get radian per second. Okay. Divide with omega m. Omega m is 2 pi f. 2 pi fm. So this is radian per second. So radian per second. So radian per second over radian per second. So beta f don't have unit. Berhati-hati. Tadi beta p has a unit, radians. But for beta f, there's no unit. It's a unitless parameter. Okay. So beta f in this example is equal to kf Vm over 2 pi Fm. Ini adalah nilai beta f. Dan untuk ini, nilai kf adalah bersamaan dengan radian per second per volt. So you're going to see later what happens if kf is equal to hertz per volt. Kita boleh juga tulis dalam sebutan yang sedikit lain, lain sedikit, seperti ini. Nampak So, if let's say kf is equal to hertz per volt, okay, hertz per volt, therefore, we can rewrite the equations to become like this. Kf Vm over Fm. So for this one, actually we divide, actually yang ini dia dapat dengan cara membahagikan dua pi atas dan bawah. So we actually get this parameter by dividing the upper and lower parameters with 2 pi. Okay, tadi kalau kita bahagikan atas dan bawah dengan 2 pi, so we will get the parameter of kf as hertz per volt. Nampak so yang ini beta f is equal to kf Vm over Fm, and in this case kf is equal to a parameter x in the unit of hertz per volt. Sama aja. So jangan confuse, jangan confuse. Remember when you derive the Fm equation, apabila kamu derive Fm equation, sebenarnya you akan dapat yang ini, beta f yang ini. Okay. Tetapi biasanya dalam pengiraan soalan, okay, normally in the calculations, in the questions to calculate some parameters, we give you beta f as this one. Okay. Kita biasanya menggunakan yang ini. Biasanya, okay, pada kebiasaannya apabila kita menjawab soalan exam, kita menggunakan yang ini. Okay, beta f is equal to kf Vm over Fm dengan syarat kf diberikan dalam sebutan hertz per volt. Okay, sekiranya kf diberikan dalam sebutan radian per second per volt, then you need to use this equation, kf Vm over omega m. So tak perlu confuse, dia benda yang sama sahaja. You need to see the parameter of kf. If you are given the kf as a radian per second per volt, then you need to use these equations. You need to divide with 2 pi Fm. But if you are given kf as hertz per volt, then you can use these equations, kf Vm over Fm. The thing is, we want to produce beta f as a unitless parameter. Itu dia punya key-nya adalah beta f mestilah unitless parameter. Remember, beta f mestilah unitless parameter. Okay, so if you don't have question about this, I will move to the next slide. Kalau ada yang tak faham, boleh tanya. Saya akan ulang semula. Tetapi kalau tak ada persoalan, saya akan teruskan. Okay. So the next parameter is frequency deviation, or known as the delta f. Ini delta f. Ni yang tadi kita belajar tadi, berapa banyak delta F tadi ya. FC plus delta F, FC minus delta F. So what is delta F? Delta F is the frequency deviation. Okay, the unit for delta F is hertz. It is defined as kf Pm. So perhatikan kelas, you can use a delta FC or you can just write delta F. We understand that this is the deviation of carrier frequency, not other frequency. Kita merujuk kepada carrier frequency. Kita tidak merujuk frekuensi yang lain. Okay, so either you want to use the delta F or delta FC, it is okay, no problem. Okay, so delta F is equal to kf Vm. So the unit is in terms of hertz. Okay, or you can find delta theta. Delta theta is equal to kp Vm. The unit is radians, perubahan fasa. Nampak Satu perubahan frekuensi, satu lagi perubahan fasa. Perubahan frekuensi dalam hertz, perubahan fasa dalam radians. Nampak So for example, a sample of transmitter assigned rest frequency 100 MHz deviated by plus minus 25 kHz. The carrier change frequency with modulation between limits of 99.975 and 100.025 MHz. Ini dia nak tunjukkan bahawa seperti ini Okay, so katalah carrier pada asalnya adalah tadi dikatakan 100 mega so ini katalah F dalam megahertz, F in megahertz. Okay, and the carrier change about 25k. So that means that this is 25k. This is over here is also 25k maximum. So berapa frekuensi maximum and negative maximum ini? Maximum and minimum, maximum and minimum. How much is the maximum frequency and how much is the minimum frequency? So here is 100.025 because this is 25 kilo. Okay, this is 25 kilo. And what is the minimum frequency of carrier? 100 mega minus 25k, so you get 99.975 megahertz. Itu yang dinyatakan di sini So both of these 25 and 25, okay, delta F plus delta F. So this is a 2 delta F. Okay, 2 times delta F, we call it as carrier swing. So in this case, the carrier swing is equal to 50 kilohertz dalam case ini. 25 kali 25 jadi 50. Okay. And then what? Okay. So this is beta F. So we have seen about this. Beta F is equal to kf Vm over omega m, or you can write it as delta Fc over Vm. So this is actually kf Vm. Okay, this is kf Vm. Okay, and remember that in this case kf must be in terms of hertz per volt. Okay, hertz per volt. And when we multiply with volt, we will produce a parameter equal to something in hertz, which is the frequency, which is the delta F. Okay. So therefore, we can rewrite the equations to be like this. Vfmt is equal to Vc sine big bracket omega ct, or you can write 2 pi fct minus delta Fc over Fm cos omega mt. So here also you can write 2 pi Fm t. Okay, boleh juga. So over here you can also write in term of beta F. Boleh juga tulis beta F macam tadi dia buat beta F. This one beta F. Okay, tak ada masalah. So in conclusion, the parameter in front of this the in front parameters parameter di depan ini the front parameters here is referring to the modulation index for FM. Apa sahaja yang berada di depan sini dia adalah parameter beta F. Remember parameter yang berada di depan cos di sini dia adalah parameter beta, modulation index. Okay. And depending on the value of modulation index beta F, we may distinguish between two cases of FM, two cases of frequency modulation. One is narrowband, another one is wideband. Ada dua jenis frequency modulation. Ada dua kategori Satu adalah wideband dan satu lagi adalah narrowband. Apa beza dia? So perbezaan antara dua jenis frequency modulation ada dua, narrowband dengan wideband. So kalau narrowband merujuk kepada dia punya bandwidth kecil, wideband merujuk kepada bandwidthnya besar. Itu dia punya perbezaan. Daripada perkataan kita dah tahu narrowband, wideband. Narrowband small bandwidth, wideband big bandwidth. Okay. Nanti kita akan lihat yang ni This is NBFM NBFM. This is WBFM, Wideband FM. Okay, kita akan lihat kemudian. Okay. And from this table, you see that from this table, the important part is the first row, row yang pertama ini for commercial FM radio broadcast, assignment frequency is between 88 until 108. Apa benda ni So this is the range of carrier frequencies. Inilah dia range carrier frequency. Dan ini adalah standard untuk FM antara 88 sehingga 108 MHz. Itu sebabnya kalau you lihat you punya radio kalau FM punya frekuensi dia daripada 88 sampai 108. And channel bandwidth. What is channel bandwidth? Channel bandwidth means that the bandwidth for each channel within this frequency assignment. For one channel, the maximum bandwidth is 200K. Untuk satu station, satu channel ataupun satu radio station, bandwidthnya adalah maximum 200 kilo. Tadi kalau you lihat sini from this range, the big bandwidth for FM is 20 M, 20 mega. Ini kalau you minuskan 108 minus 88, you will get 20 megahertz. So within this 20 megahertz, we can allocate many channels, or we can say that there are many radio stations di dalam frequency band itu. And every channels or every radio station, the maximum bandwidth is 200K. Ini kalau kita lukis sikit Okay, katalah sini adalah FM band This is FM band from 88 until 108. So this is for FM frequency band. Okay, FM berada pada julat ini. And you see that if I do a different color, okay, and within this bandwidth, we can assign many channels or many radio stations. For example, here, katalah satu radio station Okay, so this is for one channel, for example. And the bandwidth for this one maximum is 200 kilohertz. Maknanya apa? Maknanya kita boleh ada banyak radio stations dalam ni. We can have, nanti you akan lihat, kita boleh ada sehingga berapa banyak? We can have up to 20 mega divide with 200K for each radio channel. Satu radio channel, satu channel 200K, total ada 20 mega, so nanti you akan lihat bahawa 100 channel. We can assign to 100 channels at one time. Okay, 100 channels 100 channels ataupun 100 radio station. So maknanya dalam band ini daripada 88 sampai 108 kita boleh allocate up to 100 channels or 100 radio station. Dia boleh berkongsi sebanyak 100 banyak dalam tu. And if you see that here maximum deviation, so this is maximum delta F. Saya buat color lain So delta F maximum is 75 kilohertz. Okay, delta F max. Okay, so that means we cannot use more than 75. We can use up to 75 maximum by standard. And the highest audio frequency, this is for FM actually. Okay, maximum value untuk nilai FM adalah 15 kHz. So this is defined by the standard. Okay, and the rest television sound, public safety, so this is you can read on your own. Kamu boleh belajar sendiri. Tapi yang kritikal adalah baris pertama. Okay, and then what? Percent modulation parameter. Percent modulation parameter is equal to delta F actual divided with the delta F maximum by the standard. Here is 75 kHz. Okay, yang bawah ini 75 kHz. Actual is delta F actual is the delta F of your signal. Signal yang kamu pancarkan. Dibahagikan dengan delta F maximum defined by the standard. And this is supposed to be multiplied with 100%. Sepatutnya darabkan dengan 100% kerana kita nak dapat dalam sebutan percentage. Okay, for example, if a given modulating signal produce plus minus 50 kHz frequency deviation, maknanya dia punya delta F untuk signal yang dihasilkan ini adalah 50 kHz, let's say 50 kHz, and the law stated that the maximum frequency deviation allowed is plus minus 75 kHz. Ini by standard yang dibenarkan adalah 75 iaitu maximum. Therefore, we can calculate the percent modulation is equal to delta F actual divide with delta F max. Okay, so that means 50K divided with 75K multiplied with 100%. So you're gonna get 67%. So this is the percent modulation. Okay, percent modulation. Ini bukan modulation index. This is not modulation index. This is the percent modulation parameter. Okay. Example. Ini yang kita tunggu-tunggu, example. So I want you to have a calculator so that you can calculate together with me. Ini tak ada. Okay. So saya nak kamu ada calculator supaya kita boleh sama-sama kira. So example 3.2, 1 MHz carrier frequency, terus buatlah FC with a measured sensitivity of 3 kHz per volt. Nampak sensitivity parameter. So ini KF ke KP? So is this KF or is this KP? So this is in terms of hertz per volt. That means this is KF. Sensitivity parameter. Hertz per volt. So that means this carrier is modulated with a carrier modulate dengan another signal. So this another signal is actually the information signal which has a amplitude 2 volt and frequency 4 kHz. So what is this? So this is actually VM, peak amplitude of VM, and this is FM. Nampak So now what? The question asks, determine the maximum frequency deviation of the carrier. So the first question asks about delta F. Okay. So delta F is equal to apa dia? KF VM. So maknanya KF adalah bersamaan dengan 3 kHz per volt multiplied with Vm, peak amplitude of the information signal, which is 2 volt. So you will get here 6 kilohertz. Okay. And then what? Determine the modulation index. Berapa modulation index? Modulation index beta f is equal to, so macam mana ni? Kita boleh kira menggunakan, remember this kf is hertz per volt. That means kita perlu bahagikan dengan Fm, bukan omega m. Sebab you diberikan kf dalam sebutan hertz per volt. So therefore you can write either like this, kf Vm over Fm, or you can also write delta f over Fm. Since we already know kf Vm, kita dah dapat dalam soalan sebelumnya tadi So ini bersamaan dengan 6 kilohertz from the previous equation, from the previous question. Divide with Fm, Fm is given as 4 kilohertz. 4 kilohertz. So jawapannya adalah, so the answer would be 3, sorry, the answer would be 1.5. 1.5. No unit. 1.5, no unit. Okay. Next. Class, if you have question, you can ask me. If not, I will proceed to the next question. Okay. So the next question, determine the modulation index if the modulation voltage is double. So dia suruh mencari beta f, tetapi dalam kes ini modulation voltage. Apa itu modulation voltage? Modulation voltage ataupun modulating voltage dalam kes ini merujuk kepada nilai Vm. Macam mana nilai Vm? Sekiranya, okay, how much is beta f? If let's say the Vm is double, Vm now is 2 times 2 volt, so it becomes 4 volt. So how much is beta f when Vm is equal to 4 volt? Okay, so therefore beta f is equal to Kf Vm over Fm. So this is actually equal to, Kf is 3 kilohertz. So this is 3 kilohertz per volt multiplied with 4 volt divided with 4 kilohertz. So this is becomes, so 12 divided with 4, so this becomes 3. Nampak So jawapannya adalah 3. So that means if you double the modulation voltage, the modulation index will be double as well. Nampak tadi daripada 1.5 dia jadi 3. So nampak dia punya perubahan So dia berkadar terus dengan perubahan modulation voltage ataupun Vm. Okay. And then question number 4. Determine the modulation index for VMT equal to 2 cos 2 pi 8 times 10 power of t. Okay, so now you the question asks to determine the new beta f if let's say you are given a new VMT. Katalah nilai VMT diberikan yang baru So di sini adalah Vm masih 2 volt, tetapi frekuensi telah berubah menjadi 8 kHz. So these questions wants you to calculate beta f if let's say the Fm, the modulating signal frequency Fm becomes double. Macam mana kalau Fm menjadi double? Oleh itu, so kita boleh kira. So I can start calculate from here. Maybe I can write here. So now VM, so now VM is 2 volt, FM is double 8 kilohertz. So the question asks about beta F. So beta F is equal to KF VM over FM. So this is actually equal to 3 kilohertz per volt multiplied with 2 volt, okay, divide with 8 kilohertz. Okay, so this is equal to 6 divide with 8. So kita akan dapat 0.75. Boleh cuba So 3K 3K multiply with 2 divide with 8K. So you get 0.75. Siapa tak dapat boleh tanya soalan. Okay. Question number 5. Determine the FM signal mathematically for cosine carrier and cosine modulating signal. So tentukan nilai persamaan FM menggunakan persamaan cosine carrier and also cosine modulating wave. Part 4, the carrier amplitude is 10 volt. So berdasarkan soalan 4, tentukan persamaan FM sekiranya menggunakan cosine function. Diberikan nilai VC sama dengan 10 volt. Okay. So how to do that? So how to do that? Okay. So you are given these parameters. So you want to know, you want to determine VFMT. VFMT. Okay, mungkin saya nak kena guna lain ya. Tulis kat sini je lah. Okay, ini kalau tak nampak tolong beritahu Kalau tak nampak tolong beritahu So dia nak gunakan VC cos omega MT. So this is 2 pi FCT plus, okay, this is plus beta F plus KF BMT. Tadi beta kita dah dapat tadi. So we already get the beta parameter actually. So this is actually KF integral of theta prime T. Integral of theta prime T dt. Okay. So this is actually becomes, if you derive the equations, actually what you will get is VC cos 2 pi FCT plus beta F. So integral of cos you will get sine. Okay, integral of cos you will get sine 2 pi FMT. Ini kalau kita terbitkan sebenarnya dia akan jadi beta F. Ini saya langkah sebenarnya. So actually from here you can do the derivations where integral of theta t is you can get integral of KF VM integral of cos cos dt. So saya skip sebenarnya saya skip So integral of this is integral of KF VM integral of KF VM cos 2 pi FMT, and finally you will get actually what you will mungkin saya padam sikit lah. Saya padam sikit sebenarnya apabila you kamirkan tadi, mana tadi? Okay. So here is you will get a plus, because you integrate of course you will get positive sign. So this is actually 2 pi sorry you will get KF VM, sorry. So Kf Vm over 2 pi Fm, you will get here is sine 2 pi Fmt. Okay, so this is actually equal to Vc cos 2 pi Fct plus beta F sine 2 pi Fmt. Ini dia. Remember that we already get the beta F in the question number 4. Dalam soalan number 4, kita dah cari modulation index. So we just need to put inside the equations. Okay. So therefore, the equations becomes like this. Okay. So it becomes Vc cos. So Vc, how much is Vc? Is given 10 volt. So 10 cos big bracket, remember, 2 pi Fct. So 2 pi Fc. Fc is 1 mega given in the question. Okay, so 1 multiplied with 10 power of 6 T plus so Kf Vm over 2 pi Fm is actually beta F, or you can calculate beta F di sini dalam case ini. Beta F sebenarnya you boleh kira dengan cara seperti ini, Kf Vm over Fm, because we are given the value of Kf dalam sebutan Hertz per volt. So kalau you kira, sebenarnya kita akan dapat, kita dah kira berdasarkan soalan nombor 4 yang ini. Okay, where Kf is 3 kHz per volt, Vm is given as 2 volt, Fm is given as 8 kHz in question number 4. Kita dah dapat dia bersamaan dengan 0.75 in question number 4. So therefore, here is 0.75. Nampak 0.75 sine here is 2 pi sorry. Okay. Sine 2 pi, this is 8 kilohertz times 10. And then T over here. Tak nampak, saya buat rendah skala senang ya. Saya padam dulu sekejap. Saya buat di bawah lah senang saya buat di bawah dia. Eraser, I put. Sorry. Sekejap. Saya buat seperti ini Okay. So saya buat di bawah sini supaya kamu semua nampak. So 0.75 sine 2 pi 8 kHz for the FM frequency, and then close big bracket. Inilah dia equationnya. Okay. So when you answer these questions, you can begin like this macam apa yang saya buat ni daripada cos, and then we do the integral, and then finally we can put the value of beta F, because we already get the beta F. Okay, so previously you defined the FM equation without inserting the values. So sekarang kita dah masukkan nilainya. So sekarang baru you nampak bahawa FM equation ini bentuknya seperti ini. Okay, so 10 cos 2 pi Fct, 2 pi times 1 mega T, plus beta F. Beta F here is 0.75 sine 2 pi 8 kilo 8 times 10 power of 3 T. So inilah dia persamaan VFMT. So ini adalah B FM T. Okay. Ni tadi daripada bawah ke atas so jangan confuse So yang bawah ni ke atas. Okay. So do you have question about this? Ada soalan tak nak tanya? Kalau tak ada, saya akan teruskan. Okay. So the next question, the next slide. The next slide. This is the summary of FM and PM. Ini dia punya summary. Okay. So macam mana bentuk general equations like this. Okay. So this is actually beta F. Okay. So over here, this is KPVM. So this is di sini sepatutnya KVM sine sebenarnya. So this is supposed to be sine omega mt, omega m. So this is K2 lah, katalah K2. Okay. Or you can write like this. So this is M or beta F. So normally for the FM and PM, we use a beta instead of M. Ini diambil daripada buku lain sebenarnya. If you read in other literature books, they also use M for the modulation index. Wayne Thomas's book used beta. So tak ada masalah. Okay. So here is okay. And then okay. So this one I think you can read on your own. Okay. Don't memorize this. Tidak perlu hafal. Cukup kamu faham macam mana nak menggunakannya. Because your final exam is open book, so you don't need to memorize this. Okay. Next one. This is about how many channels. Well, the calculation of how many channels. Okay, ini pernah ditanya. So this kind of this example that have been asked previously in the exams, pernah ditanya dalam exam. Okay. So commercial radio FM band. So keseluruhan FM band itu berada pada 88 hingga 108 MHz. Each station or each channel allotted to a frequency deviation of plus minus 75 kHz. Okay. That means this is 150 kHz. So this is actually kilohertz, 150 kHz. 75k multiplied with 2, you will get 150 kHz, which is the carrier swing. And additional 25 kHz of guard band above and below. So macam mana bentuk dia? So kita lihat sekejap. So let's say I draw this. Saya nak tunjukkan So macam mana bentuknya. So let's say this is F in megahertz, paksi F, F in megahertz. And it is said that the FM band from 88 until 108. Okay, so if you draw this one, it is supposed to be something like this. Okay, so the question now asks how many radio stations that we can allocate in this FM band from 88 until 108. Okay, and given in the standard that the maximum frequency deviation is 75 kHz and a guard band of 25k. So ini ada dinyatakan dalam table yang tadi yang ini. 75K of delta, 75 kilohertz of delta F max. Okay. So let's I use a different color. Okay. So now we want to calculate, katalah satu station seperti ni. Sorry. Okay. So let's say one radio station. Okay, center over here, and this radio station, by standard, it has a frequency deviation of 75K. Okay, this is 75. Okay, another here is 75. Okay, so that means kalau saya lukis dia macam ni. So this is for one radio station. Okay, one radio station. Okay. And if you see that 75 and 75, so the distance here is actually 150. However, you see that, however, if you see from the previous table, it is said that channel bandwidth maximum is 200 kilohertz. So where are the remaining 50 kilohertz? Mana baki lagi 50 kilohertz? Okay. So where are the other 50 kilohertz? Okay. So so 50 kilohertz is allocated for the guard band 25. So actually here another 25, 25. Another 25 over here. Okay, so that's why you get like this. So therefore the total distance is 200 kilohertz. What is guard band? Guard band is like a empty space that we allocated in the band so that it is not overlap with the adjacent channel. Bermakna channel ini tidak boleh berfungsi pada guard band itu untuk mengelakkan interference with the adjacent channel. Okay, so guard band ini boleh dikatakan seperti ruang kosong, macam pagar lah sebenarnya, contoh untuk memisahkan antara satu channel dengan channel bersebelahan. Okay, untuk mengelakkan berlakunya interference. We don't want the adjacent channel to be overlap. Kalau overlap, maka you akan dapat signal yang macam mana, bunyi signal yang bercampur-campur. Kalau you pernah naik kereta, you tune to one radio station, you move to another place, and when you move to another place, you will see that there's a overlapping of one channel with another channel, seperti mixing. You tak boleh nak bezakan ini macam ada gangguan channel lain. That is when the signal is overlapping. Okay, so dalam satu kawasan, okay, dalam satu kawasan kita boleh allocate. So now we are talking about one area. Kita tak boleh cerita satu Malaysia. We are talking in one area. For example, in Batu Pahat. Contohlah sana Batu Pahat. Batu Pahat. So this in Batu Pahat, we have a base station for the radio, for example, that cover the area of Batu Pahat. Okay, so we can allocate this FM band from 88 until 108 to 100 radio station within Batu Pahat. Kita tak boleh kata satu Malaysia because it is too big. It is because this band is defined with the area. Okay, that's why if you listen to a radio, the frequency is changes when you move from one place to another place. Kalau saya dengar sinar FM di Batu Pahat, frekuensinya dalam 96 MHz. If I move to Kuala Lumpur, the frequency will be different. Okay, so that one is based on because this frequency assignment is based on area, kawasan tertentu. Okay, dia bukan kawasan yang besar. Okay, so what I want to show that this is the guard band. This is the guard band. Okay, so the radio station should not operate at this guard band. It is to separate from one channel to another channel. So you see that the total is 200 kilohertz for one channel. So how many stations we can allocate, or how many channels we can allocate in this bandwidth from 88 until 108? Berapa banyak? So therefore, we can allocate number of station or number of channel to be equal to 108 minus 88 megahertz divide with 200 kilohertz of one channel. So therefore, we can get 100. Kita akan dapat 1%. So this is also one of the favorite question being asked in the final exam. Okay, 100 channel or station. Ini banyak kali ditanya dalam exam, soalan bonus. Okay, so we can allocate 100 radio station or 100 channels within the FM band from 88 until 108 megahertz. Okay. Okay, next. Narrowband FM. So narrowband FM, so the word narrow here means that the bandwidth is small. So how much smaller? How much small is it? It is between 10 to 30 kilohertz roughly in general. So kalau bandwidthnya antara 10 sampai 30, tu kita katakan kecil lah untuk frequency modulation. Okay, so modulation index are keep near unity so that the FM bandwidth can be determined in a similar manner as the AM system. So for narrowband FM, the way we calculate the bandwidth is actually 2 times FM. Later you're going to see that narrowband FM frequency spectrum looks similar with the double sideband full carrier. Nanti kita akan lihat dia punya spektrum itu kelihatan hampir sama seperti a double sideband full carrier. Okay, so this narrowband FM is widely used for the mobile radio systems for the police, fire and taxi services. Okay, and then assuming that VCT is VC cos omega CT, VMT is equal to VM cos omega MT. So dalam kes ini dia akan gunakan general equation menggunakan cos. Okay, so therefore when we define the VFMT, it is equal to VC cos omega CT plus beta F sin omega MT. So kalau kita gunakan cos dan cos, kamiran daripada cos adalah positive sin. Itu sebabnya tambahkan dengan sin. So plus beta F sin omega MT. Okay. So now the issue is we want to show the equations for the narrowband FM. Remember in narrowband FM, what happened is that beta F is small. Okay, beta F adalah kecil kerana bandwidth yang dihasilkan ini adalah kecil. Sebabnya beta F dan bandwidth adalah saling berkait. Nanti you akan lihat bahawa nilai beta F akan menentukan nilai bandwidth. Okay, later you're going to see that the higher the beta F, the higher would be the bandwidth. Nanti juga kamu akan lihat bahawa if the beta F is smaller, the bandwidth would be smaller. So therefore, beta f is proportional to the bandwidth. Nanti kita akan lihat juga. So in this case, beta is small, usually between less than 0.25. So dikatakan di sini bahawa nilai beta adalah kurang daripada 0.25 kerana dia sangat kecil dalam Narrowband Fm. So therefore, dikatakan di sini bahawa ini ada approximation yang dia buat, ada dua. So dikatakan di sini bahawa approximation untuk cos beta f sin omega mt approximately equal to 1. Whereas sin beta f sin omega mt approximately equal to beta f sin omega mt. Apa benda ni? So these two approximations will be used to approximate the general equation for narrowband. Kerana kalau you lihat di sini ini adalah kalau lihat daripada general equation ini ada A plus B nampak So omega ct adalah A parameter, beta f sin omega t adalah B parameter. Kenapa saya buat A B Kenapa? Sebabnya kita nak menggunakan trigonometry identity. Trigonometry identity for BC cos A plus B. Remember trigonometry identity untuk cos A plus B. We can define this using a trigonometry identity. You see that cos A plus B, using a trigonometry identity, it is equal to cos A cos B minus sin A sin B. Ini adalah trigo identity. So therefore, we can rewrite the equations to become cos omega ct minus VC sin omega ct beta f sin omega mt. Macam mana dapat benda ni? Okay. So therefore kita lihat kembali cos A adalah VC cos omega ct. What is cos B? Cos B, cos of this yang pertama ini. Saya padam dia. So cos B is this one cos of B. Ini adalah B Cos B is approximately equal to 1. So oleh itu ini menjadi sebenarnya darabkan dengan 1 sebenarnya. Okay. And then what? Sin B. Sin B, if you see from this approximation, sin of B, ini B Ini tadi kita dah buat ni B, so ini B lah, B parameter. Sin of B is approximately equal to beta f sin omega mt. So ini masukkan dalam yang tadi, yang sini. So sin of B equal to beta f sin omega mt. Nampak So therefore, kita boleh kembangkan lagi equation ini because we have another sin and sin. Sin and sin, according to trigonometry identity, it is equal to this. I think you know about this. Cos A minus B minus cos A plus B divided with 2. So kita kembangkan lagi equation ini, dia menjadi seperti ini, yang bawah. Okay. So kalau you lihat yang pertama tadi VC cos omega ct plus 1/2 beta f VC big bracket cos 2 pi FC plus FM. So ini sepatutnya terbalik sikit Oh, sebab ada negatif di sini so dia jadi plus kat sini. So jangan keliru sebab di sini ada negatif, so dia jadi seperti ini, terbalik daripada inilah. Okay. So 1/2 beta f VC cos 2 pi FC plus FM T minus cos 2 pi FC minus FMT. So yang ini adalah USB, yang ini adalah LSB. And from this equation, we can draw the frequency spectrum. Kalau kita lukis frekuensi spektrumnya, maka dia akan kelihatan seperti ini. Okay, ada 3 komponen, FC, upper sideband, lower sideband. Okay, so upper sideband located at FC plus FM, lower sideband is located at FC minus FM. And the amplitude is, according to the equation, berdasarkan equation, VC, dan amplitude di sini adalah half of beta F VC, which is this one. Nampak When we want to draw the frequency spectrum, we need to know the complete equation first. Then we can draw. Don't straight away jump to drawing. Jangan terus lompat kepada drawing. You perlu faham apakah dia punya equation terlebih dahulu. Okay. So up to here, if you have question, you can ask. Okay. So you see that Narrowband FM, I can say that it is similar, setara dengan double sideband. Setara bukan sama, setara. Okey, setara bukan. Maksudnya dia punya setara dari segi jumlah spektrumnya. You akan nampak ada 3 spektrum. Okey, yang mana jarak bandwidth-nya the bandwidth is 2 FM. Okay, and if you want to calculate the power, of course, power P total. In this case, it is equal to PC plus PLSB plus PUSB. Okay, so ini adalah VC square over 2R. This is 1/2 beta F VC kuasa 2 dibagikan dengan 2R plus 1/2 beta F VC square over 2. So this is if you want to calculate the power. Okay. Next, Wideband FM. So wideband FM means that the frequency modulation signal has a wider bandwidth. So perkataan wideband merujuk kepada bandwidth. Bandwidth yang dihasilkan adalah besar. Berapa besar? Bergantung. Bergantung kepada nilai beta. The larger the beta F, the larger would be the bandwidth. Okay. So for the okay, if you see that here, in order to compute the spectrum of angle modulation with, let the data F. Okay, so from the general equation here, VC cos, dia menggunakan cos, so tak ada masalah nak guna cos boleh, nak guna sin boleh. But if you use cos, make sure you use a VMT also in term of cos, so that easy for you to do the to define the equations. So dalam kes ini dia menggunakan VMT dalam sebutan cos. So when you integrate cos, you will get positive sign. Okay, positive sign. Okay, so here is beta F sin 2 pi FMT. So ini adalah general equation untuk FM. Okay, so the issue now for the wideband FM, the value of bandwidth is determined by the value of beta. So kita tak boleh define secara, kita tak boleh tentukan secara langsung berapakah nilai bandwidth. We need to see a table. Kita perlu lihat menggunakan table Bessel. How to find the bandwidth. So you will learn here about Bessel table. Perhatikan kelas. So this is very important. Okay, you need to understand how to read the table. Okay, perhatikan Ni kalau tak faham, ni terus tanya Please ask question if you don't understand. Because you need to know how to use this table. Because of course final exam will use this table. Biasa memang akan pakailah benda ni So from this table, you see that the first column here is modulation index, beta F. Okay, beta F, if you see from here, it moves from 0 until 8, from small until bigger. Okay, and you see from column number 2, column here, until the last column, it is actually a J parameter. What is J parameter? J parameter is what we call as the relative amplitude. J ini adalah relative amplitude. Yang mana J0 for the carrier component and J1 until J10 is for the sidebands. So maknanya kalau kita nak lihat so maknanya kalau kita lukis dia punya paksi, maknanya so J0 pada FC dan dia boleh ada sehingga 10 pasang 10 pair. So J10 So this table shows up to J10, sideband number 10. So that means we have 10 upper and 10 lower. Okay, ada sepasang. Okay. So the values inside, the values here. Perhatikan kelas, perhatikan. The values here, okay, you see that it has some values from J0 until J10. And you see that here this dash, all of this dash maknanya dia tidak ada, there's no sideband. Tidak ada sideband pada pada bahagian itu. Contoh, example. Let's say beta equal to 1 for example. Beta equal to 1, so you have a carrier component and you have up to 1, 2, 3. That means we have 3 pairs of sidebands for beta F equal to 1. Maknanya apa? Kalau kita lukis, untuk beta F bersamaan dengan 1, okay, untuk beta F equal to 1, so we have 3 pairs of sidebands. Nampak So this is J0, J1, J2, J3. Okay, this is also J1, J2, J3. And the value here, okay, the value here is the relative amplitude. What is the relative amplitude? Relative amplitudes, okay, Jn, whatever, n, is equal to Vn, the real amplitude, divide with Vc. Ini maksud dia. So actually Jn does not have any unit. It's a unitless parameter. Dia adalah nisbah antara voltage sebenar dibahagikan dengan carrier voltage. Okay. And if you see, let's see the last one, beta F equal to 8. Macam mana kalau beta F sama dengan 8? So if beta F is equal to 8, you see that we have up to 10 pairs of sideband. Maknanya kita ada sehingga 8 pasang sideband. Sorry. For beta F equal to 8, we're gonna have up to 10 pairs of sideband. Ada 10 pasang. Macam yang saya lukis ke atas ni lah. Okay, daripada J0 sehingga J10, so we have 10 upper and 10 lower sidebands. Ada 10 pasang. Nampak Maknanya, the higher the value of beta, okay, the higher the value of beta, the larger would be the bandwidth. Nampak So, berapa pasang sideband yang muncul berdasarkan nilai beta. Okay. Another one is about the negative value. So nilai negatif-negatif ini sebenarnya bukan merujuk kepada magnitudes. yang kecil, tetapi dia sebenarnya merujuk kepada perubahan fasa. Berlakunya perubahan fasa, okay, 180 degrees tu sebab dia tulis dia punya polarity bertukar daripada positif kepada negatif. Okay, so it is also explained here that the negative is actually referring to the 180 degree of phase inversion. Berlakunya perubahan fasa sebanyak 180 darjah, itu sebabnya nilainya menjadi negatif. Okay, so that negative is actually the polarity to show the phase shift, 180 degree. Okay, and in this table, dalam table tersebut telah mengabaikan semua nilai sideband yang kurang daripada 0.01. That means if there's a sideband less than 0.01, it is not inserted in the table. Maknanya table tadi dia telah mengabaikan nilai sideband yang kurang daripada 0.01. Maknanya apa? Maknanya sideband table ini kurang tepat sedikit, agak kurang tepat. Kalau you lihat table sebenar, akan ada values yang kurang daripada 0.01. So no problem. That one is not a big problem, because in this example, we eliminate the values less than 0.01. Nanti dia akan ada kesan sedikit, tidak banyak, very small difference. Okay, you're gonna see later. But previously, long time ago, we use a real table yang mana ada banyak value. Contoh kelas contoh di sini mungkin ada nilai yang kurang daripada 0.01 tetapi tidak dimasukkan. Kalau you lihat table sebenar, dia akan ada nilai walaupun kecil. Okay. And from the previous past semesters, kita menggunakan table yang inilah. So lebih mudah untuk pelajar kerana table ini memang ada dalam nota. So kita akan pakai table ini di dalam final exam. Okay. So you see that from here, okay, ini ditunjukkan di sini So you see that ini sehingga 6 up to 6. So if you see from the table 6, I can say that maybe this is about this one. So for beta F equal to 3, you're gonna have up to 6 pair of sideband. Kalau beta F sama dengan 3, akan ada 6 pasang sideband. Contohnya seperti ini. Nampak So okay. So you see that ini ada penerangannya, saya telah terangkan. The important part is this one, that the table has been omit all the values less than 0.01. And another thing is about the negative values, which is actually corresponding to the 180 degree phase shift. Yang lain you boleh baca sendiri. Okay. Okay, this is the Bessel function graph. So this is actually the real graph that we use to get the values in the table. Table tadi, dia mengambil nilai berdasarkan graf ini sebenarnya. Inilah dia Bessel graph. Okay. How to use this Bessel graph? So we need to have a ruler. Kita perlu ada pembaris. Okay. So siapa ada pembaris, boleh keluarkan pembaris kamu. So if you have ruler, you can come out with a ruler now. Okay, saya nak tunjukkan. Let's say you have a ruler, kamu ada pembaris, dan kamu boleh gunakan pembaris kamu untuk melihat nilai J berdasarkan nilai beta. So paksi X adalah Modulation Index beta F, paksi Y adalah nilai J. Okay, so tadi katalah nilai beta F bersamaan dengan 1 So you can use your ruler. Okay, gunakan ruler kamu. Kamu boleh ni perhatikan bahawa dia akan cross pada J3. It will also cross at J2. It will cross at J1 and it will cross at J0. Ini kena guna pembaris baru nampak lurus. So these cross values are the values inside the table. Nilai dalam table itu adalah nilai yang kita garis silang ni. So kalau beta F1 kita guna pembaris, di mana dia akan bersilang itulah dia nilai J. Berapa nilai J0, J1, J2 dan also J3. That one is we use a ruler. Okay. But we haven't asked this thing. Kita tak ada menyusahkan pelajar sehingga perlu guna pembaris untuk mencari nilai J. Actually we give you the value of J based on the table. Okay, ini saya nak tunjukkan macam mana sebenarnya nak mencari nilai J berdasarkan Bessel graph. So you kena ada pembaris. Okay. So table akan diberikan kepada pelajar. So mudah. Okay. So this is the spectrum. Okay, so you see that the larger the larger the beta, lagi besar nilai beta, maka lagi besar nilai bandwidth. Akan ada banyak sidebands. Okay, the larger the value of beta, you're gonna get more sidebands, and the bandwidth gonna be bigger. Nampak Next, transmission bandwidth of FM signal. Ini dia. Macam mana nak tentukan nilai bandwidth for the wideband FM? Okay, so the bandwidth of wideband FM can be determined using two methods. The first method is using a Bessel function. Method pertama untuk menentukan bandwidth menggunakan Bessel function. So it is equal to 2 times N FM. 2 kali N FM dalam sebutan Hertz. Where N is the number of significant sideband. N di sini adalah bermaksud jumlah pasang sideband. Berapa pasang sideband. Okay, bukan jumlah sideband, dia adalah berapa pasang sideband. Contoh. Okay. So for beta F equal to 1, we gonna get up to 3 pairs of sideband. Ini akan ada sehingga 3 pasang sideband. Bermakna pada beta F sama dengan 1, nilai N sama dengan 3. Kenapa? Kerana pada beta F equal to 1, we can produce up to 3 pairs of sideband, 3 pasang sideband. Perhatikan yang lain. If beta F is equal to 8, we're gonna produce up to 10 pairs of sideband. That means N equal to 10 for beta F equal to 8. Nampak So maknanya nilai N bergantung kepada nilai beta. When you want to find the value of N, first you need to know what is the value of beta. Kalau tak tahu nilai beta, kita tak boleh cari nilai N. Okay, we need to know how much is the beta. Okay. So we can find the bandwidth using these equations. Okay. So example. Ini contoh So calculate the bandwidth occupied by FM signal with a modulation index of 2. So beta F is equal to 2. And the highest modulating frequency is equal to 2.5 kHz. So ini merujuk kepada nilai FM. Determine the bandwidth. So the bandwidth using a Bessel function, it is equal to 2 times n times Fm. Okay, so the issue now is how much is n? So n you need to see from the table because the table we are given a beta f equal to 2. Okay, kalau kita lihat table untuk beta f bersamaan dengan 2, this one beta f equal to 2, so we're gonna get up to 4 pairs of sideband, 4 pasang sideband. So n equal to 4. Therefore, n equal to 4. Okay, so put inside the equations. Okay, so n here is 4. Okay, so 2 times 4 times 2.5, so we get 20 kilohertz. Selesai. Okay, so this is the bandwidth. Okay. Another method to calculate the bandwidth is using a Carson's rule. Ini kaedah yang kedua untuk mengira nilai bandwidth. So here the bandwidth by Carson tadi kita sebut yang tadi ni kita biasanya kita akan buat bandwidth Bessel. Kita buat macam ni biasanya. Bandwidth Bessel. For this one normally we write like this bandwidth Carson. Okay, it is equal to 2 delta F plus 2 Fm, or you can write 2 delta F plus Fm. So perhatikan di sini, dia tidak bergantung kepada nilai n. It is not we don't need to find beta F as well. Beta F pun kita tak perlu cari. Kerana dia hanya berkaitan dengan delta F dan juga Fm. And you're going to see later that bandwidth by Carson is actually approximate bandwidth. Dia bukan nilai bandwidth yang tepat. Dia adalah approximation bandwidth. Nanti you akan lihat bahawa nilai ini kurang daripada bandwidth by Bessel. You will see later that bandwidth Carson is less than bandwidth Bessel. Okay, so bandwidth by Bessel is more accurate. Okay, bandwidth Bessel is more accurate. Example. Okay, for example, you are given a delta F frequency deviation, delta F equal to 5K and maximum modulating frequency 2.5. So this is Fm. Calculate the bandwidth. So this is bandwidth by Carson. Okay, bandwidth Carson is equal to 2 times this is 2 times Fm plus delta F. So dalam kes ini dia buat this is Fm plus delta F. Okay, so if you plus and then multiply, so you get 15 kilohertz. Perhatikan So sebenarnya kalau dilihat di sini okay, kalau kita kira kalau kita congak nilai beta F sebenarnya bersamaan dengan delta F dibahagikan dengan Fm. So this is actually 5 kilohertz divide with 2.5 kilohertz, which is equal to 2. Nampak Kalau kita guna Bessel, bermakna kita akan dapat berdasarkan beta F sama dengan 2. Kalau kita guna Bessel kita akan dapat n sama dengan 4. Kalau n sama dengan 4, that means bandwidth by Bessel akan bersamaan dengan 20K. Tetapi apabila kita menggunakan bandwidth by Carson, we only get 15 kilohertz. Nampak So ini sebenarnya soal example ini adalah sama macam example sebelumnya yang mana nilai beta bersamaan 2. and the value of significant sideband n equal to 4. Okay, so kalau guna bezel kita akan dapat 20K. However, if we use a bandwidth by Carson, we get 50 kilohertz. So comparing both, you see that you can see the Carson will give smaller bandwidth. Ini ada dinyatakan di sini. Okay, so kalau ada soalan sila tanya. So biasanya dalam exam we ask both, calculate bandwidth by bezel compared to the bandwidth by Carson. So you can see the difference. Okay. Example. So example 3.4. Okay, example 3.4 for an FM modulator with a modulation index beta f equal to 1 and a modulating signal equal to Vm t Vm sine 2 pi 1000 t. So this is actually Fm. Okay, and you are given carrier frequency is 500K, 500 kilohertz. So this is FC. Okay, and you are given a VC equal to 10. We don't know how much is VM. VM kita tidak tahu. Macam mana nak buat ni? So make sure you have a calculator. So now beta F equal to 1. Determine number of sets of significant sideband. So how much is the value of n? Okay, so this is based on the Bessel table. For beta f equal to 1, we're gonna get number of significant sideband equal to 3. Kita akan dapat 3 pasang sideband. Okay. So here the number of significant sideband n is equal to 3. And then what? How much is the amplitude? Nampak? So now from the Bessel table, actually we can get the relative amplitude. Daripada Bessel table tadi kita boleh cari nilai J0, J1, J2, J3. Okay. So kalau you lihat dalam tadi J0 J0 adalah 0.77, J1 is 0.44, okay, J2 is equal to 0.11, J3 is equal to 0.02. Ini dalam table, based on the table. So now what? Now we want to determine how much is the amplitude. Okay, and we can determine the frequency as well. Okay. So dalam exam biasanya kita galakkan pelajar untuk membuat dia punya table lebih mudah. So kita buat macam ni lah. Okay. So here is the value of J, Jn, okay, which is J0 until J3. Okay, so here is J, here is the amplitude in voltage, and then we can determine the LSB, and we can also determine the USB. Okay, so for the first one, J0 is equal to 0.77. Okay, so the amplitude V0 is equal to, remember J is equal to, Jn is equal to Vn over Vc. So that means Vn is equal to Jn multiplied with Vc. Okay, so V0 is equal to 0.77 multiplied with VC is equal to 10. So that means 7.7 volt. Nampak? And here dia berada pada center frequency FC. So ini tak perlu isi lah sebab dia berada di tengah. FC dia berada pada FC iaitu FC equal to 500 kHz. Okay. And then what? J1. So J1 is equal to 0.44. Ini boleh kira bersama saya. So V1 is equal to 0.44 multiplied with VC, which is 10. So you get 4.4 volt. Okay. How much is the value of LSB? So LSB is equal to FC minus FM. Okay. So here is equal to berapa tadi? FC adalah 500K. So 500K minus 1K. So this is actually 499. Okay. Over here is FC plus FM, which is equal to 500K plus 1K. So this is 501 kilohertz. Nampak? Similar with J2. Okay. So J2 ni saya terus ringkas. J2 0.11. So V2 is equal to 0.11. So this is equal to 1.1 volt. So this is located at dia terletak di mana? So that means this is FC. So this is the second. Okay, the second. That means FC minus 2 FM. So therefore, this is 500K minus 2 kilohertz. So this is 498 kilohertz. This is FC plus 2 FM. This is 500 plus 2K. So this is 502 kilohertz. Okay, and the last one is so the last one is J3 is equal to 0.02. So therefore V3 is equal to 0.02 multiplied with 10. So we get 0.2 volt, 0.2 volt. So LSB is equal to FC minus 3 FM, which is equal to 500 minus 6 kilohertz. So we get 494. Sorry, bukan 6 sorry. 3 times 3 FM minus 3 FM, so minus 3. So 497 kilohertz. Sorry, bukan 6 Dia sebenarnya FC minus 3 FM. FM is 1K. So 500 minus 3K, so 497. Manakala untuk USB adalah FC plus 3 FM. So this is equal to 500 plus 500K plus 3K. So we get 503. 503 kilohertz. Nampak So this is their amplitudes. Okay. So dalam kes ini saya telah memperoleh amplitude dan juga dia punya frekuensi sekaligus. Saya cari amplitude dan saya cari di manakah lokasi frekuensinya. So dah dapat. Okay. So I already get the values for amplitudes and also for the frequencies. Okay, for the carrier, the amplitude is 7.7. For the first sideband, 4.4 volt, located at 499 kilohertz and 501 kilohertz. Second sideband, amplitude is 1.1, located at 498 kilohertz and 502 kilohertz. Sideband number 3, the amplitude is 0.2, located at 497 and 503 kilohertz. Nampak eh? So we already get the amplitudes and also the frequencies. Now what? The next question asks, draw the frequency spectrum showing their relative amplitude. Showing their relative amplitudes. So kalau dalam case ini, okay, ada dua jenis soalan yang boleh ditanya, sama ada nak menunjukkan relative amplitude ataupun amplitude. Okay, so saya tunjukkan sekejap. So when you draw, okay, so we have carrier, we have the first sideband, second sideband, third sideband. Okay, so we have here okay. So when you draw, remember to have this axis label. So this is F versus perhatikan kalau soalan tanya relative amplitude, that means I want to know J versus Jn versus F. That means I can just put here like this. So this is if plot relative amplitude versus frequency. Okay. So maknanya Jn versus F. However, if the question asks, draw the amplitude spectrum. Maknanya apa? Maknanya kalau amplitude spectrum, ni saya padam saya padam dulu. Kalau amplitude spectrum, that means we need to label the real amplitudes. Okay, what is the real amplitude? The real amplitude we already find here, which is this is 7.7 at the carrier component. This is 4.4. This is 1.1. This is 0.2. 4.4, 1.1, 0.2. So this is actually voltage versus frequency. And remember, we need to label the frequency as well when we draw the spectrum. So here is 500. So katalah ini adalah kilohertz. Let's say this is a kilohertz. So this is 501, 502, 503. This is 499, 498, 497. Okay, so for these questions, it asks about relative amplitude. So you should put J instead of V. Okay, so jawapan sebenarnya sepatutnya kita tulis dalam sebutan J. Okay, 0.77, 0.44, 0.11, 0.02. So this is the way we draw. Remember, macam saya nyatakan sebelum ni, apabila ditanya soalan drawing, first we need to know whether your drawing is correct or not. Second, labeling. Adakah you label dengan betul? Label di sini adalah ada dua. Satu, paksi. Yang kedua adalah nilainya, iaitu frekuensi dan juga dia punya amplitude. So if you draw like this, full marks. Okay. So for these questions, saya guna color lain. So it is actually 0.02, 0.11, 0.44, 0.77, 0.44, 0.1, 0.02. So this is actually J. Okay, J versus F for relative amplitude versus frequency. Nampak Ada soalan nak tanya? Do you have question to ask about this? So siapa tak faham boleh tanya soalan. If you understand, we can move to the next example. Okay. Okay, tak ada soalan So saya harap kamu boleh faham Kalau ada soalan terus tanya saya This is a simple example Ini soalan yang mudah. Okay. Next example. So if you understand this, I will move to the next example. Example 3.5. Okay, example 3.5. For an FM modulator with a peak frequency deviation delta F equal to 10 kilohertz. Okay, delta F 10 kilohertz. Modulating signal frequency FM 10 kilohertz. VC 10 volt, carrier 500 kilohertz. Determine the actual minimum bandwidth from the vessel. Okay, so maknanya disuruh cari bandwidth by vessel. Itu sebab dia katakan actual perkataan actual ini merujuk kepada bandwidth vessel, bandwidth sebenar. So bandwidth by vessel is equal to is equal to 2 times N times Fm. Okay, so we need to know how much is N. Okay, how much is N? So N can be determined based on the value of beta. So kita kena cari beta terlebih dahulu. Beta F is equal to delta F divided with Fm. So this is equal to 10k divided with 10k equal to 1. So based on the Bessel table, for beta equal to 1, you will get N equal to 3. Ini daripada table So boleh lihat kalau beta F sama dengan 1, kita akan dapat N, number of significant sideband equal to 3. So that means we're going to have 3 pairs of sidebands. Okay, ada 3 pasang sideband. So therefore the bandwidth by Bessel, this is equal to 2 times 3 times 10 kilohertz. So this is 60. Okay, 60 kilohertz. Okay. And then what? Okay, ini jawapannya 60 Find the approximate minimum bandwidth using Carson's rule. So the question asks how much is bandwidth by Carson. This is 2 times delta F plus Fm. So this is equal to 2 times delta F is 10 plus Fm is 10. So 10, 10, 20 times 2, you get 40 kilohertz. Okay. And then what? Plot the output frequency spectrum for the Bessel approximation. Soalan ini dia tidak menyatakan secara spesifik. Adakah ini relative amplitude ataupun amplitude spectrum? Okay, plot the relative amplitude spectrum. That means you need to plot J versus F. If the question asks plot amplitude spectrum, that means you need to plot V versus F. Okay. So katalah ini adalah V versus F, okay, because this is not saying about is this amplitude, is this a relative amplitude. So dalam example ini, katalah kita nak mencari amplitude spectrum. Okay, let's say this is a amplitude spectrum. Okay, so that means when we need to determine the amplitude first. Okay, we need to determine the amplitude first. So you see that berdasarkan yang tadi kita boleh guna table yang tadi sebenarnya. Kita ada we have J0 equal to 0.77, we have J1 equal to 0.11, 44, J2 is equal to 0.11, J3 is equal to 0.02. This is based on the table. Okay, and when we want to find the amplitude, okay, when we want to find the amplitude, so we can draw a table actually. Okay, we can draw a table. Okay, so this is Gn. Okay, and then this is amplitude. Okay, this is LSB. This is the USB. Okay, so the first one is J0. The amplitude is 0.77 multiplied with VC is equal to 10. Okay, so this is multiplied with 10, so we get 7.7 volt. Okay, so J1, and then here we don't have the LSB USB because this is the center. And then this is a J1. J1 is 0.44 multiplied with 10. Okay, so we get 4.4 volt. The location of frequency is equal to Fc minus Fm. So this is 500K minus 10K. So we get 490 kilohertz. Okay, 490 kilohertz. And here is Fc plus Fm. So we get 510 kilohertz. J2 is equal to 0.11 multiplied with 10 volts, so we get 1.1 volt. Here is Fc minus 2 Fm, so this is 480 kilohertz. Okay, 2 kali Fm, 2 kali 10 K, so 20, so 480. Here is Fc plus 2 Fm equal to 520 kilohertz. And then for J3, this is equal to 0.02 multiplied with 10, so 0.2 volt. So this is Fc minus 3 Fm equal to 470 kilohertz. This is Fc plus 3 Fm equal to 530 kilohertz. Okay, so when you want to draw, ini saya padam yang atas ni. So let's say this is an amplitude spectrum. That means seperti ini, so F is equal in kilohertz, for example, and this is the amplitude spectrum. That means this is volt. So we have here is this is 500. Okay, with the amplitude of 7.7, and then we have 3 pairs of sidebands. Okay, so this is located at 510, 520, 530. This is 490, 480, 470. Okay, and the value is 4.4, 4.4, 1.1, 0.2, 1.1, sorry, 4.4, 1.1, 0.2. Selesai. Full marks. So that means I draw correctly. I have 3 pairs of subbands. I label the axis. I label the values as well. Nampak class? Don't use ruler when you draw the spectrum. You are going to waste a lot of time. Okay. The thing is we want to know whether the drawing is correct or not. And you label it. Okay. Ada soalan? Do you have question about this? If you don't have questions, I will move to the next slide. Okay, saya akan pergi kepada slide berikutnya, iaitu berkenaan dengan deviation ratio. Okay, deviation ratio is the minimum bandwidth. So, okay, deviation ratio is actually the worst case modulation index. Okay, deviation ratio ini adalah worst case modulation index, bermakna modulation index yang tertinggi yang boleh dihasilkan. Okay, so deviation ratio ini juga menyatakan keadaan worst case yang mana pada ketika itu bandwidth adalah paling besar disebabkan oleh modulation index adalah maksimum. Okay, so this is what they call as the worst case modulation index, equal to the maximum peak frequency deviation divided with the maximum modulating signal frequency. Bermakna delta F max divide with Fm max. So this is actually beta F max, which is defined as DR, deviation ratio. Dia tidak ada unit, no unit. Okay. Example. So example, let's look at the above part. Determine the deviation ratio and bandwidth for the worst case. The widest bandwidth modulation index for an FM broadcast band transmitter with a maximum frequency deviation 75K and maximum modulating signal frequency of 15 kHz. Ini dia dah beri delta F dengan delta F max and also Fm max telah diberikan. Okay, so abaikan soalan yang bawah ini. So the question asks about DR. So DR is equal to delta F max divide with Fm max. So this is equal to 75 kilohertz divide with 15 kilohertz. So ini sama dengan berapa? Ini sama dengan berapa ni? 75 bagi 15. So we get 5. Okay, so this is the answer, 5. Okay. So in this case, the widest bandwidth is has a deviation ratio equal to 5. Okay, simple. So abaikan soalan yang bawah ini, buang. Okay. So let's go to the next topic, power. The favorite topic. Ini adalah soalan favorite, power. We like to ask about power. Okay. So you see from here, the way they calculate the power is equal to 1/2 VC square, summation from minus infinity to infinity, Jn square, Jn square. So this is a function of Bessel. So nyatakan bahawa kita tambah semua komponen daripada hujung, daripada bahagian negatif daripada bahagian minimum kepada bahagian maksimum. Okay, kita tambah semua komponen. We plus all the components. Okay, so you see that persamaan power ini mana? R. Sebenarnya ada nilai R yang mana R in this example it is assumed as unity, bersamaan dengan 1. Kita anggap dia bersamaan dengan 1. Sebenarnya persamaan power masih sama, V square over R masih sama. Okay. So you see that here, kenapa suddenly J tidak ada? Suddenly there's no J. So where's the J? Okay. So it is said that Bessel properties, one of the Bessel properties say that summation of quadratic J from minus infinity to infinity would be equal to 1. Ini adalah property daripada Bessel. So Bessel kata hasil tambah kuadratik J daripada minus infinity kepada infinity menghasilkan nilai 1. Okay, so therefore you will get VC square over 2, which is this is actually equal to PC. Ini sebenarnya ada R lah kat sini which is actually equal to PC, carrier power. Maknanya total power for the frequency modulation is equal to the carrier power. Nampak total power bersamaan dengan carrier power. How is it supposed to be like that? So we will calculate later. Okay, ada persamaan dia. So PC carrier power is equal to VC square over 2R. Ini macam tadi lah So ini dia letak R lah, so jangan confuse sebenarnya tadi ada R tetapi dia anggap R sama dengan 1. Okay, don't be confused. Persamaan power di mana-mana masih sama, tidak ada perubahan. Okay, so di sini letak R lah. Okay, so VC square, so this is actually the PC. Okay, and remember as I told you before, when we want to calculate the power based on the spectrum, if you remember, we have a few spectrum over here. Okay, we need to add all the power component. Number 1, 1, 2, 3, 4, 5. For example, like in this example, I need to add all the component powers. Kalau kita nak cari total power, kita kena tambahkan semua power. Remember that. Itu yang kita belajar sebelum ni. Okay, so you see that here, P total is equal to P0, P at the center, plus power of the sidebands. Power daripada pasangan sideband. Itu sebabnya didarabkan dengan 2. Kerana kita ada upper and lower sideband. Remember, we have upper and lower. So that's why we need to multiply with 2. Senang cerita, kita kena tambah semua sekali. Okay. So therefore, P0 is equal to V0 square over R. Daripada mana V0? V0 is equal to, this is Vn. Vn is equal to Jn multiplied with Vc. Okay, so V0 is equal to J0 multiplied with Vc. Sama juga dengan V1. V1, kalau V1 sama dengan J1 darabkan dengan Vc. V2 sama dengan J2 darabkan dengan Vc dan seterusnya. Okay. So you see that here. So you see that for V1 here is J1 Vc, J1 Vc, J1 Vc square. So ini adalah J2 Vc square, J3 Vc, and this is Vn. Sorry. So this is J3 Vc Jn. Okay. So if you do the quadratic, maknanya akan ada J square Vc square over 2R. Ni So maknanya dia akan jadi, ni saya ambil contoh yang ini contohlah dia akan jadi J1 square VC square over 2R. Yang mana ini adalah PC, carrier. Itu sebabnya dia jadi seperti persamaan yang bawah ini. Okey, dia jadi persamaan seperti persamaan bawah ini. So J0 square PC, ini sebab ini adalah J0. Okay. This is J0 VC. So J0 square VC square over 2R, which is J0 square PC plus 2, this is J1 square PC. Ini yang saya tunjuk contoh yang tadi. Sama juga dengan yang seterusnya. J2 square PC, J3 square PC, and so on until Jn square PC. Where you will see that this is actually equal to PC. Nampak Sebenarnya kalau you tambahkan semua, dia akan jadi sama dengan PC, equal to PC. So in the exam, if you write the total power for FM equal to PC, also correct. Tak salah, betul. Okay, juga betul. Okay, tidak ada masalah. So that's why you need to see the total marks. Kalau total marksnya kecil lah, kita guna yang ni dah simple lah, habis selesai. Okay, so biasa kalau banyak-banyak ni kita nak mula-mula kita suruh lukis, barulah kita kira power. So you can use this complete equations. Okay, dan ayat bawah ini dinyatakan total power in the carrier and the sideband components approximately equal to the unmodulated carrier power. Nanti you akan lihat bahawa tadi saya sebut PT equal to PC secara teorinya macam ni theoretically is like this. However, when you do the calculation using the Bessel table in your notes, you akan dapat PT approximately equal to PC. Hampir sama dalam perbezaan beberapa titik perpuluhan sahaja. Kenapa? Kenapa macam tu? Why? It is supposed to be like this. But why it is approximately equal? Hampir sama, beza titik perpuluhan sahaja. Kenapa? Disebabkan oleh ini. Kalau kamu gunakan table tadi dia berlaku approximately disebabkan ini. Kerana kita telah mengabaikan nilai kurang daripada 0.01. J kurang daripada 0.01 telah dibuang daripada table. Itu sebabnya you dapat approximation hampir sama dengan PC. Beza titik perpuluhan saja dia bukan beza nilai, dia beza titik perpuluhan. Sikit je, very small. Theoretically, it is equal to PC. But when you calculate using your table, you will get approximately equal to PC. Hampir sama, very close. Okay. Nanti ada example yang menunjukkan perbezaan ini So inilah dia. So this that's all for today. Later next week we're gonna see the example for power and so on. Mungkin next week saya dah boleh habiskan kot topik FM So that's all for today. Itu saja pada hari ini. Dan you can open your QR code scanner. Boleh open QR code scanner. Okay, after scan you can go out and you can go to the next class So dah scan, you boleh keluar dan pergi kelas berikutnya.
Alright, so thank you.
Okay, welcome.
Assalamualaikum. Terima kasih doktor.
Terima.
Thank you, doktor.
Okay, welcome.
Terima kasih doktor.
Thank you, doktor.
Sama.
Thank you doktor.
Doktor,
Ya,
saya Yunis Felicia, doktor.
siapa nama?
Yunis Felicia.
Dr. Abdul Muiz, boleh doktor?
Muiz lagi.
Terima kasih banyak doktor.
Okay, sama.
Muhammad Hakimi doktor.
Doktor.
Ya, tadi siapa? Nama tadi siapa?
Yunis Felicia, nombor 6.
Yunis. Nombor 6. Yunis. Okay, Yunis.
Thank you, doktor.
Okay, welcome.
Ahmad Wafi, nombor 2 doktor.
Okay,
Terima kasih doktor.
sama.
Okey doktor.
Yang lain macam mana? Dah scan dah?
Doktor,
Ya,
saya ada soalan.
Ada soalan? Okay.
Regarding due date project, is it extended to 4 December or still on 27 November?
Due date tu saya lanjutkan untuk memudahkan pelajar, tetapi kalau you dah siap, you boleh terus submit.
Oh, so the extended due date is still valid lah.
Saya extendkan supaya you ada masa untuk buat laporan untuk siapa yang tak siap lagi lah. But if you already complete the report, you can submit, no problem.
Okay, sure. Thank you, doktor.
Okay, so tak perlu tunggu sampai 4 bulan. Kalau you siap hari ni, terus hantar. No problem.
Alright, doktor.
Okay. So, 3 orang absent. Siapa lagi 3 orang ni? So, that's all.
Doktor,
Ya.
saya Muhammad Azan. Saya tak boleh nak scan sebab buka
Syaidi.
kat phone. Betul.
Okay, dah.
Alright, okay.
Okay, dah. Itu saja. Anyone? Any more? Okay, 3, 2, 1. Okay, so saya anggap semua dah settle. So I will stop
Terima kasih,
sharing.
doktor.
Okay, sama.
Terima kasih doktor. Assalamualaikum doktor.